So I'm Alexey Ignatiev. I'm a senior lecturer at the Faculty of Information Technology of Monash University. And here is the poster for our DSAI 22 paper called Using MaxSAT for Efficient Explanations of Tree Ensembles. This work was done in collaboration with a few colleagues of mine, including Peter Stuck at Monash and Yasinidze and João Marques Silva in France, in Toulouse. So this work is about formal explainable AI. So the motivation is very simple. We have a machine learning model which we want to understand, and we want to see why it makes some certain predictions. For instance, in this example, we have a machine learning. It can be some deep neural network, for instance, that predicts this picture is showing a cat. And our task is to understand what exactly are the features in this picture that are responsible for this concrete prediction, why it's a cat. Well, the problem with machine learning these days is that although it's extremely powerful, nobody really understands how it works in practice. Like, there are some, of course, ideas, but to make sense of machine learning models in general is a very difficult problem that we need to solve in practice. And there are some regulations, say in the EU, where an individual is entitled for an explanation if a decision is made automatically that affects them, right? And so in this concrete work, we focused on what's called gradient boosted trees, these kind of models, and we compute what's called formal abductive explanations. So what is a formal abductive explanation? That's basically a subset of features that is sufficient for a certain prediction. For instance, if we look at this boosted tree and we have an instance that assigns some of the features some way or another, to make a prediction, we we run this instance in each of the trees. There will be some paths that fire, and there will be a leaf assigned, for instance, this and this. If we assign petal length, say 1.4, anything else can be assigned to other features. And then we want to understand which of the features, petal length, sepal width, petal width, and so on, which of them are responsible for the prediction in this concrete case. Well, an obvious choice of a logical reasoning to compute formal explanation would be satisfiability modular theories. In this concrete case, modular the theory of linear arithmetic over reals. And this is because we can easily encode each of the trees logically. That will be just a bunch of paths. Each path is a conjunction of literals. And in the end, we would need to use about this argmax function to decide which class we select. In this work, we decided to consider another logical formalism, namely, instead of doing with this SMT formulation, because this is a linear constraint, sometimes it's difficult to reason about, and the difficulty basically depends on the number of trees we have in this ensemble, and it can be hundreds and thousands of trees, so it's quite challenging in practice. So what we propose to do instead, we propose to consider the same encoding for the boosted trees, subject to an additional aspect we consider in our work. Basically, we replace this linear constraint with an objective function. It looks like this. It's one sum minus another sum. The idea is very simple. We replace a decision oracle call to an SMT solver with an optimization oracle call to a pure propositional oracle, basically an optimizer for propositional satisfiability called maximum satisfiability. So there are lots of details in this paper on how to make this work efficiently. Namely, we use core-guided MaxSAT solvers, and actually we propose a way to make core-guided MaxSAT incremental, which is very important in practice, because if we make a series of MaxSAT calls, we don't want to start the MaxSAT solver from scratch every single time, because the number of features is maybe significant in practice, and the number of calls we make equals the number of features. We also proposed the novel weight stratification mechanism, which is very important in practice in MaxSAT solving, and we also developed two ways to terminate early, which allows us to stop the MaxSAT solver earlier without proving optimality of the solution. So the main insight which helped us to develop this kind of approach is that if we consider this objective function, we can formulate a definition of an abductive explanation respectively. Basically, it's a subset of feature values is an explanation if the optimal value of the objective function is negative, right? And we can compute this optimal value and see if it's negative or positive. This gives us an answer to this kind of query. So in our work to compute a formal abductive explanation, given an already constructed optimization problem formulation, we can apply the standard linear traversal approach to, or deletion-based approach to extract an abductive explanation, which is shown here. So we have our model encoded into MaxSAT, we traverse the set of features, and then we make entailment oracle checks. Well, each entailment oracle checks is done by making a series of MaxSAT oracle calls. A series means that we need probably to make them work incrementally. Otherwise, we will need to create a lot of MaxSAT oracle calls from scratch, which is very expensive in practice. And this algorithm shows how to make a MaxSAT solver, if we're talking about co-guided MaxSAT solvers, incremental. Right? So what we propose to do is to reuse the unsatisfiable cores detected in the previous MaxSAT calls in the future in the following MaxSAT calls. So what we propose to do is, if we have some unsatisfiable cores detected previously, we first try to use those, if possible, and only afterwards, when those are exhausted, we proceed by detecting more unsatisfiable cores if necessary, which also requires us to record the cores we detect now for the future MaxSAT calls. So this is done efficiently, and detection of unsatisfiable cores can be done by applying unit propagation. So it's pretty effective in practice, and our approach also allows us to reason about various sets of assumptions. So basically, we have a MaxSAT formula, and then to extract an explanation, we need to vary the set of assumptions given to the MaxSAT solver. This is why we have to make a series of oracle calls. And depending on the set of assumptions, we may or may not detect some of the unsatisfiable cores found previously. So I guess if you're interested, talk to me or talk to the people in the optimization group of FIT at Monash. Thank you very much for your attention.